Integrated problem number 4. So we're going to use this time to talk about answer these questions involving a diamond-like abrasive. The diamond-like abrasive silicon carbide is made by reacting solid silicon dioxide with graphite at 2000 degrees Celsius to produce solid silicon carbide and carbon monoxide gas. So all of these questions are again going to relate to this single reaction that's occurring. So let's break this down into pieces. So let's start again. Diamond-like abrasive silicon carbide can be made by reacting silicon dioxide with graphite at 2000 degrees Celsius to produce solid silicon carbide and carbon monoxide gas. So write a balanced chemical equation that represents this reaction. So we're reacting solid silicon dioxide, so that's a molecular compound, so it's silicon, Si, dioxide, O2, and it's a solid. Reacts with graphite. Graphite is an allotrope of carbon, so it is just carbon as a solid, and it just has its this specific form of graphite. That's going to react to form solid silicon carbide and carbon monoxide gas. So those are the basic components of this reaction. Now we have to worry about it being balanced. So if we look at silicon, we have one silicon on this side, one silicon on that side. If we look at carbon, we have, or oxygen, excuse me, we have two oxygens on this side, one on that side, so we need to add a 2 in front of the carbon dioxide. So now we have 2 carbons and 2 oxygens. So now the silicons and the oxygens are balanced. Now if we look at carbon, we have 1 carbon on this side as a reactant and 1, 2, 3 total on this side. So we have to have a 3 there. So now that it's implied that we have 1 silicon dioxide plus 3 carbons as graphite gives us 1 silicon carbide plus 2 carbon monoxides. Okay. Assuming that carbon has a mass number of 12 and silicon has a mass number of 28, how many protons, neutrons, and electrons does each atom of carbon and silicon have? Right? So we have carbon 12 and silicon 28. And we want to know the number of protons, the number of neutrons, and the number of electrons. For the number of protons, that number comes from, that's the atomic number, comes from the periodic table. Right? So if we look at carbon, carbon has an atomic number of 6, so its proton number must also be 6. Silicon has an atomic number of 14, so its number of protons must be 14. The mass number, remember, tells us the number of protons plus the number of neutrons. So our mass number, 12, has to equal the number of protons plus the number of neutrons. So we take 12 minus 6, so this is equal to 6. Again here, 28 has to be 14 plus the number of neutrons, so it's going to be 28 minus 14, which is equal to 14. For this to be neutral, or have no charge, the number of protons has to equal the number of electrons. So since we're not having either one of these charged, the number of protons or electrons has to be 6, because the number of positively charged protons is 6. Same with this. We have 14 positive protons, we must have 14 negative electrons. Okay. The next thing is calculate the temperature, this 2000 degrees Celsius, into Fahrenheit and Kelvin. So we're going to take 2000 degrees Celsius and convert to either Kelvin or Fahrenheit. Remember from our equation sheet here that to calculate degrees Fahrenheit, we're going to take 5/9 the temperature in Celsius plus 32. So degree F is going to equal 9/5, excuse me, the degree Celsius plus 32. To calculate Kelvin, we're going to take the degrees in Celsius plus 273.15 to get our response. Right? So to solve this, we're going to take 9/5 times 2000 plus 32. Do that math, and out pops. So this is going to give us one significant digit. We add them together. We go to the fewest number of decimal places, which is 0. So we're going to get 3632 degrees Fahrenheit. For this other one, we're going to take the 2000 degrees Celsius plus 273.15, add those two together. Again, we're doing addition, so we go to the one at the fewest number of decimal places, 0 and 2. So we're going to end up with a number that has no decimal places. Again, remember, Kelvin is an absolute scale, so there's no degrees symbol there. Okay. Next. Identify all the species in the balanced reaction as an element or compound. If it is a compound, tell it whether it's molecular or ionic. Right? We have the balanced chemical reaction over here. What I'm going to do is just copy it to the top on this one so that we have it to look at. So we're going to take SiO2 plus 3 C's goes to SiC plus 2 COs. So for each one of these, we're going to list whether it's a compound or an element. And then if it's a compound, is that a molecular or ionic compound? So we have SiO2, carbon, or graphite, excuse me, and silicon carbide, and carbon monoxide. So the first part, is this an element or a compound? This is a mixture of two elements, so this has to be a compound. Carbon is by itself, so that's an element. Silicon carbide is 2 elements, so that's a compound. And carbon monoxide is also more than 1 element, so that is a compound. The next question is whether each of these that are compounds, are they molecular or ionic? Again, based on its position on the periodic table, we have silicon and oxygen. This is going to be a molecular compound. Elements, we don't have to answer that question. Silicon and carbide, also both nonmetals, or metalloids and nonmetals, so this is molecular. And carbon and oxygen, we have silicon and carbon, and carbon and oxygen, all nonmetals. So all of these are examples of molecular compounds. Calculate the molar mass of each of these. Again, so we're going to take SiO2, we're going to look at carbon, we're going to look at silicon carbide and carbon monoxide. For all of these, the molar mass is going to be equivalent to what we were referring to earlier as the molecular mass, which is going to be the sum of the individual masses. So off of the periodic table, For silicon and oxygen, we're going to look at the mass of silicon, which is 28.09. We have 1 silicon. We'll multiply that by 1. Add that to the 2 oxygens. Oxygen has a mass of 16.00. So we're going to take the silicon times the 2 oxygens to give us a molar mass equal to 60.09 grams per mole. So for every 1 mole of this compound, we're going to have a mass of 60.09. Carbon, look, it's by itself, but it still has a molar mass. It's just going to be that of carbon, which is 12.01 grams per mole. Silicon carbide, we're going to take the mass of silicon, which is 1 times its 28.09, plus the 1 times the mass of the carbon, 12.01. Do that math and we get 40.1 grams per mole. And for carbon monoxide, take the 1 times the mass of carbon plus 1 times the mass of oxygen to give us 28.01 grams per mole. Right, so it's a similar process to what we had before when we were talking about molecular masses. For the reaction, or if the reaction was performed starting with 68 grams of silicon dioxide, what mass of silicon carbide do we have? Again, I'm going to start by rewriting this balanced chemical reaction so that we're going to take silicon oxide plus 3 carbons goes to silicon carbide plus carbon, 2 carbon monoxides. Right? Because in order to convert from one compound to the other, we have to know how they're related within this reaction. This balanced chemical reaction tells us not only the number of atoms or molecules that are reacting, it's also the number of moles. So for every 1 mole of silicon dioxide that reacts, we get 1 mole of silicon carbide. Or for every 1 mole of silicon dioxide that reacts, we have to react that with 3 moles of carbon. Right? So in general, we're going to go from the mass of silicon dioxide to moles of silicon dioxide to moles of silicon carbide to mass of silicon carbide. So using the same dimensional analysis that we've been doing, that's the steps we're going to take. So we're going to start with this 68 grams of silicon dioxide. We need to convert from grams to moles. We're going to use its molar mass. So its molar mass of silicon dioxide was 60.09 grams. So that sticks 60.09 grams for every 1 mole of silicon dioxide. So if we have 60.09, or if we have 1 mole, that's going to weigh 60.09 grams. So now we're left with moles of silicon dioxide. From the balanced reaction again, we say that for every 1 mole of silicon dioxide that reacts, we get out 1 mole of silicon carbide. And we don't want moles, we want mass. We have to use the molar mass again. For silicon carbide, it was 40.1. So for every 1 mole of silicon carbide, we get 40.1 grams of silicon carbide. Do the math, multiply everything on top, divide the things on the bottom. We get a mass. Again, we have 2 significant digits here, so our final answer is going to have 2 significant digits. So we end up with 45 grams of silicon carbide. So the same sort of dimensional analysis we've done before, we're just using this idea that the balanced chemical equation gives us the relationship of moles. Next, calculate the number of atoms of carbon and silicon involved in this reaction. So the reaction we're talking about is up here. So when we react 28 grams or 68 grams, how many atoms of carbon and silicon are involved? Well, if we look here, when we solved this problem, we saw that we formed 45 grams of silicon carbide. So we can, if we figure out how many grams of silicon there are, atoms of silicon there are in this, that'll answer our question. So we're going to start with 45 grams of silicon carbide. And we want to go to mole or atoms of carbon. Right? So the first thing we have to do is go back to moles using the molar mass. So 40.1 grams of silicon carbide gives us 1 mole of silicon carbide. Right? We want a number of atoms, so we have to then use the ratio here. Right? We don't want silicon carbide, we want just carbon. So we can say for every 1 mole of silicon carbide, we get 1 mole of silicon involved. We don't want moles, we want the atoms. So remember, for every 1 mole of silicon, we're going to get 6.022 times 10 to the 23rd atoms of silicon. So that gives us, when we do that, we see that we get 6.8 times 10 to the 23rd atoms of silicon. Right? We can do something very similar for the carbon, again starting with the 45 grams of silicon carbide. We can say that for 1 mole of silicon carbide is 40.1 grams of silicon carbide. And now remember that this relationship here is not always we can consider it not just in terms of moles, but in terms of atoms and molecules. So I'm going to switch these 2 steps. Right? So we say 1 mole of silicon carbide is 6.022 times 10 to the 23rd molecules of silicon carbide. And for every 1 molecule of silicon carbide, we get 1 atom of carbon. Right? So when we do this, we essentially just switch these 2. Because they're equivalent, we find that we also get 6.8 times 10 to the 23rd atoms of carbon, which makes sense because in this molecule, for every carbon, we have a silicon, and every silicon, we have a carbon. So if we repeated this again, SiO2 plus 3C goes to SiC plus 2CO. If we did this again with 86 grams of graphite, how much silicon carbide would we have? Again, we're going to do the similar process. This time we're going to start with 86 grams of carbon. From our atomic mass from earlier, our molar mass, we know that carbon has a molar mass of 12.01. 12.01 grams for every 1 mole of carbon. From the balanced chemical equation, for every 3 moles of carbon that we react, we get 1 mole of silicon carbide. And we don't want moles, we want a mass in grams, so we're going to say for every 1 mole of silicon carbide, we have a mass of, again, 40.1 grams. do that math, and out will pop our mass of silicon carbide. Again, two significant figures, so we get 96 grams of silicon carbide. So the mass we're getting is going to be related to how much we start with. Again, we can do this same process to figure out how many atoms of carbon and silicon. We're going to repeat that very same process we did here in number 7. We're just going to use now this 96 grams of silicon carbide. 40.1 grams of silicon carbide is 1 mole of silicon carbide. For every 1 mole of silicon carbide, we have 6.022 times 10 to the 23rd molecules. And for every 1 molecule of silicon carbide, we get 1 mole, or 1 atom of silicon, or 1 atom of carbon. I'm only going to do this calculation once to save on time, but when we do that, we see that we get 1.4 times 10 to the 24th atoms of silicon. Only difference in the carbon, though, is in this last step. We would see that we get the same number, 1.4 times 10 to the 24th atoms of carbon, because, again, they're in a 1-to-1 ratio. So let's look at this last one. If a plant is producing this abrasive, wanted to produce 254 kilograms of silicon carbide a day, how much carbon dioxide would they produce in a year? Right. So we're producing 254 kilograms of silicon carbide every day. And we want to go to carbon dioxide in a year. So the first thing we have to do in order to relate silicon carbide to carbon monoxide, we have to go through the balanced chemical equation, which relates either atoms or moles. So we have to convert this to moles. But first we have to go from kilograms to grams. 1 kilogram is 1 times 10 to the 3rd grams. And then, as we've done several times now, for every 40.1 grams of silicon carbide, we get 1 mole of silicon carbide. From the balanced chemical reaction, for every 1 mole of silicon carbide, we have produced 2 moles of carbon monoxide. So for every 1 mole of silicon carbide, we get 2 moles of carbon monoxide. And we want to know a mass. So again, going back to our molar masses from before, for carbon dioxide, we get 28. 1 mole of carbon monoxide is 28.01 grams. The last thing, so this, if we stopped our calculation here, our units tell us that we would end up with grams of carbon monoxide per day. The question wanted how much in a year, so we have to convert this day to year. So there's 365 days in 1 year. So when we do that, multiply the things on the top, divide the things on the bottom. We get 1.2. Again, now we're going to have 3 significant digits. So 1.29 times 10 to the 8th grams of carbon monoxide per year.